Good day to all. And I would like to convey wish you happy new year to all the aspirants who are serious about the exams this new year. Most of the chemistry content will be provided for sure. And definitely we will go with the new content and high impact on your examination. This is the channel called World of Competitive Chemistry, where you can achieve, where you can search whatever content you are requiring for in the entire chemistry field. You can get the maximum content with the quality information over there, so that we will go with the session for the day. The Nobel Prize in the field of chemistry 2011 was awarded to Dan Sachsman for the discovery of quasi-crystals. Here, the concept is said to be quasi-crystals. The discovery of quasi-crystals was done by a single scientist called Dan Sachsman, and he contributed his research outstanding invention, that is a quasi crystal, a new kind of crystal dimension he provided with, so that he got the world recognition with the prestigious Nobel Prize in the field of chemistry for the year 2011. He is the scientist contributed alone for the quasi crystal invention and exploration as well, Dan Sichman. And Royal Swedish Academy of Sciences accorded laureated the scientist Dan Sichman with the Nobel Prize in the field of chemistry for 2011 for the discovery of quasicrystals. Let me give the brief info regarding this Dan Sichman. He is called technician Israel Institute of Technology, Haifa, Israel. This is the address which resembles his a recognition for his research. He did his research from this institute. Are remarkable mosaics of atom. Quasicrystal, we find the fascinating mosaics of the Arabic world reproduced at the level of atoms, regular patterns that never repeat themselves. However, a configuration found in the quasicrystal was considered impossible, and Dan Sichman has to fight a Fate's battle against established science. The Nobel Prize in the Chemistry 2011 was fundamentally altered how chemists conceive the solid matter, right? So here, Arabic world produced at the level of atom, regular patterns that never repeat themselves. Whatever regular patterns we have in the atomic level, so that they will not be repeated further. However, configuration found in a quasi-crystal was considered impossible. Whatever they are arranging, whatever dimensions they are showing, which are impossible for the hypothesis earlier. But after the invention of these quasi-crystals, the impossibility come into the reality, possibility, right? On the morning of 8th April 1982, an image counter to the laws of nature appeared in Dan Sichman's electron microscope. In all solid matter, atoms were delivered to be packed inside the crystal symmetrical pattern that were repeated periodically over and over again. For scientists, this repetition was required in order to obtain a crystal, right? So whatever atomic dimensions are there, that should be repeated, so that what they can notice periodicity in the properties can be observed, right? That is the symmetrical pattern of the atoms in the systematic crystal. That is the normal possibility. But Suchman's image, however, showed the atom, his crystal, were packed in a pattern that could not be repeated. So that is the kind of crystal where atom pattern will be there, which will not be repeated combination, repeated configuration. Rather, it is the new dimension always. One atom to another atom, there is a certain kind of uniqueness he fabricated. Such a pattern was considered just as impossible as creating a football using only six cornered polygons. When a sphere needs both five and six cornered polygons, right? So if you want to make a atom, a kind of crystal, for example, let me assume a football. Football is having hexagons and pentagons in such a manner so that entire football manufacturing is possible. But assume only hexagons are there, by eliminating all the pentagons from that. That means 5-membered rings are discarded, only 6-membered rings are located. How can we construct that football? That is also possible. Hence, this is the new dimension in the field of chemistry, that is the solid manufacturing, regular crystalline manufacturing with the unique dimensions repetition of the atoms was discovered, which is called quasi-crystal. His discovery was extremely controversial. In the course of defending his findings, he was asked to leave his research group. However, his battle eventually forced scientists to reconsider their conception of the very nature of the matter. A periodic mosaics, such as those found in the medieval Islamic mosaics of the Alhambra Palace in the Spain, Darby Imam Shrine in the Iran, have helped scientists to understand what quasi-crystals looks like at an atomic level. In those mosaics, as in quasi-crystal, the patterns are regular, they follow mathematical rules, but they never repeat themselves. So many historical evidences also noticed with the quasi-crystals. One of the thing is Alhambra Palace, which is located in the Spain, and Darby Imam Shrine, which is located in Iran. These are the simplest example for the what quasi-crystals, where the repetition of themselves atoms are not yet all possible, but they are in the tradition to follow mathematical rules, and regularity is noticed over, but repetition is absent, right? When scientists describe the Sedgman's quasi-crystal, they use the concept that comes from the mathematics and art, the golden ratio, right? Mathematics to the art golden ratio will be there, that taken into the consideration in order to exemplify this quasi-crystal concept. This number has already caught the interest of mathematicians. Ancient Greece, as it often appeared in the geometry. Quasi-crystal, for instance, the ratio of various distances between atoms and are related to golden mean, right? In the quasi-crystal, ratio of various distances, whatever atomic distances, dimensions they are present, they are existing in the golden ratio, and moreover, golden mean they appealed. This is the way they explorated with the quasi-crystals. A new era of crystalline chemistry was introduced by the technician known as the Dan Sedgman, who is accorded with the Nobel Prize alone in the field of chemistry, Don Sedgman, in the year 2011. And the question is question number 2 is collected from International Education of Cambridge Assessment. Ammonia is used in the manufacturing of nitrogen-containing fertilizers. Which of two of these compounds are present in the fertilizers? Fertilizer is composed by potassium chloride, sodium phosphate, sulfur dioxide is able to give a kind of chemical composition which is imposed with this ammonia. So whenever ammonia, potassium chloride is there, ammonium, potassium chloride will be there. That is the NPK are the most essential macronutrients everybody aware about. So that potassium chloride is essential, and sodium phosphate is if it is mixed with ammonia, so that we will get ammonium phosphate, which is also the nutrient fertilizer for the croplands. And neither sulfur dioxide mixed up with ammonia in the proper ratio, ambient ratio we can say, so that ammonium sulfate will be originated, that is another nutrient material for the croplands. Here straight fertilizers are nothing but which are required in the maximum quantity primary plant nutrients. They are said to be nitrogen, phosphorus, and potassium, NPK we said. So N for nitrogen, potassium is given with K, phosphorus is given with P. NPK are the essential macronutrients. And these are essentials available in the form of either urea, ammonium sulfate, potassium chloride, and potassium sulfate. All these are composed, all these are generated by means of mixing ammonia with potassium chloride, sodium phosphate, and sulfur dioxide. And that is provided over here. Analysis of the products, whenever ammonia treated with sulfur dioxide, formation of ammonium sulfate is possible, so that sulfur dioxide reaction is essential. And go with Go with the sodium phosphate. Upon treating with ammonia, ammonium phosphate will be formed. Here you can notice ammonium potassium. Ammonium potassium chloride is also the required essential, so that these three are indicated with the tick mark. For question number 2, potassium chloride, sodium phosphate, sulfur dioxide are the essentials to be mixed with ammonia in order to make the nutrient fertilizer, right? Fertilizers are the nutrients for the crop plants. This is the way you can go for the flow chart. And urea, ammonium sulfate, potassium chloride, potassium sulfate are the important nutrients directly used as the growing material, so that we can say these are called straight fertilizers, right? So we entered into the question number 3, which is collected from JEE Advanced 2016, paper 1 question. It is National Testing Agency conducted this exam. Mixture showing the positive deviation from Raoult's law at 35 degrees centigrade. Raoult's law is a kind of the property which is related with the colligative properties. Solutions are able to observe this Raoult's law. And where the positive deviation you can notice for this, that is given with the option carbon tetrachloride methanol, carbon disulfide acetone. These two are the A and B are the correct answers. Let's go with this. Carbon tetrachloride and methanol, carbon disulfide with acetone. How can we explain this? Let's see. When intermolecular attractions between the two components A and B are present, then A and B, a mixture is the same as AA and BB. AA means a homo kind of nature. Both are having equal nature. Either BB is also having equal nature. So at that condition, if two atoms are having equipotent, equally competing to each other, that is said to be ideal solution. When intermolecular attractions between A and B are smaller than the AA or BB, intermolecular attractions are smaller. That means weak interactions are noticed than AA and BB, so that the compound is having high vaporization, easily vaporized, so that boiling point will be less. Less boiling point is noticed for them, and those compounds are exhibiting positive deviation from the Raoult's law. Whenever interaction between AA and BB is AB is higher in comparison to them, so that less vaporization, high boiling point, you can notice those compounds are exhibiting negative deviation from the Raoult's law. Negative deviation is noticed. At that instance, methanol molecule having polarity and having tendency to form the hydrogen bonding. Whenever mixture of methanol and carbon tetrachloride, their composition is there, but carbon tetrachloride is non-polar, so that though this is polar, no provision to form the hydrogen bonding, so that this able to vaporize and show the positive deviation from the Raoult's law. This is the way it can be explained. Whenever the condition number 2, acetone. Acetone is purely nonpolar, higher intermolecular attractions, dipole-dipole interactions are noticed over, and carbon disulfide directly in contact with acetone, so that the interactions get decreased. So dipole-dipole interactions get lowered up, so that whenever interactions are lowered, the molecule is becoming volatile. Whenever volatile molecule is there, boiling point will be low. Low boiling point shows the positive deviation. But benzene and toluene, when benzene toluene mixture is there, benzene is a non-polar, toluene is non-polar. When non-polar interaction is there, there is no kind of mixing, there is no kind of interaction. That is said to be an ideal solution. Phenol and aniline. Phenol is polar, aniline is also polar compound. Both are interacting in the higher extent, larger extent interaction can be noticed. Higher interactions due to intermolecular hydrogen bonding, so that whenever hydrogen bonding is possible among these two compounds, they are interacting, so that boiling points will be higher, vaporization will be lower, and they are able to exhibit negative deviation in the Raoult's law. Negative deviation can be mentioned. Carbon tetrachloride with methanol, so that higher the vaporization lower the boiling point, so that positive deviation. Carbon disulfide with acetone, lesser the interactions, higher the vaporizations, and the lower will be the boiling point, positive deviation. So that A, B are the correct answers. Benzene and toluene, non-polar compounds are together, so that no way interaction, and this is said to be ideal solution. Phenol with the aniline, both are polar and polar, strong interaction with the hydrogen bonding called intermolecular hydrogen bonding, which able to show the lower vaporization, higher interaction of hydrogen bonding, hence high boiling point. High boiling point gives rise to the negative deviation. So entire things got covered. A and B are positive deviating options. For question number 3, A, B are the correct answers. Go with the question number 4. The correct statement for the cubic close packed 3-dimensional structure. Cubic close packed 3-dimensional, the question is picked up from solid state chemistry. And this is the kind of session where we are going to discuss about cubic close packed system is also denoted as a face-centered cubic lattice. And regarding this, few correct statements to be identified. First of all, we will go with the entire concepts, whatever they mentioned over, so that we will pick which are correct exactly. Okay. The number of nearest neighbors for the atom present in the topmost layer are 12. The efficiency of the atoms packing in this system will be 74%. The number of octahedral and tetrahedral voids per atom, there is a logic. This is completely logical sentence over there. Octahedral and tetrahedral voids per the atom are 1 and 2 respectively. The unit cell edge length is 2 root 2 times to the radius of the atoms. The unit cell edge length in comparison to the radius of atom, it will be 2 root of 2. The expected answers are B, C, and D. A is incorrect one. Let's see with what are the all these close packing system of identical spheres. Crystals, of course, three-dimensional objects. All the crystals are three-dimensional in nature. They can be extended in the x coordinate, y coordinate, z coordinate, so that we can say 3D structures. Crystals are 3D structures. But we will begin by exploring properties of array through two-dimensional space, because it is impossible to place the crystals on three-dimensional plane on the paper or display screen, so that for our convenience, we can mold them into two-dimensional space. This will make easier to develop some of the basic ideas. Complications for getting your visualization of 3D, something that I find requires a bit of practice. Always representing the molecule in three-dimensional way is somewhat difficult to process. Moreover, we have to go for the skilling process for making the 3D pictures always. That's the reason why our convenience, we are making the 3D pictures into 2D. Square packing is noticed over. Hexagonal packing also noticed. Hexagon. Here you can notice hexagon like this. Okay, this is the kind of square packing. This is called hexagonal packing. Okay. If we go from world of marbles to the atoms, which kind of packing would the atoms given element prefer? So here so many solids are known to you. So many solid compounds, marble flooring will be there with you. And so many kind of building blocks will be there. Household materials will be there. Daily life application solids will be there. Edible things will be there. Industrial machineries will be there. Wherever you are using such a kind of solids, what kind of solid structure they are adopting, what is preferential structural convenience for the molecules, that part we have to know about. Okay, so among all, we are going to discuss about a cubic close packed system, which is abbreviated as a CCP. CCP arrangement atoms are in such a manner. The unit cell consists of 4 layers. 4 layers are there. Here you can you can see 1 layer, 2 layers, 3 layers. Backside, one more layer is existing, so that it is a 4-layered structure. The top and bottom layer contains 6 atoms at the corner hexagon and one of the atom at the center of each hexagon. 6 atoms per top layer is consisting 6 atoms, but they are saying Topmost layer is containing 12 atoms. So you can strike out this option. Topmost layer in the cubic closed packed system is having only 6 atoms. That's the reason why A option is striked off. Move on to any other. Cubic closed packed CCP, hexagonal closed packed HCP, two efficient lattices when we considering packing. The packing efficiency of both of these are 74, which means 74 of the space is filled. In the entire 100%, 74% of the sphere is completely filled by the atoms in case of the CCP lattice. Okay, so that cubic closed packed system having packing efficiency 74%. 74% occupied by the atoms and remaining how much? 26% vacant voids or vacant empty place will be there. So this is the way B option will be cleared. Move on to any the number of tetrahedral and octahedral voids in CCP are 8 and 4. So this part you can clearly observe. Tetrahedral voids are 8, octahedral voids are 4 for this CCP lattice. Okay. So number of particles are 4. Number of particles are 4. 4 atoms if present, 8 tetrahedral voids, 4 octahedral voids will be there, right? Hence, number of tetrahedral octahedral voids are 8 and 4 respectively. Okay. Number of tetrahedral voids are twice the number of particles. Number of particles are 4, no? Always tetrahedral voids, you have to double them. So, if the particles are 4, you can put 8 for tetrahedral voids. Always octahedral voids exactly is equal to number of atoms. Number of atoms are 4. Octahedral voids also 4. This is the clear hint for this calculating tetrahedral voids and octahedral voids. Always octahedral voids belong equal to number of atoms. Tetrahedral voids is equal to twice the number of atoms. Okay. From this, the logic we have to find out is, again we are repeating, CCP contains number of atoms are only 4. Octahedral voids also 4, because whatever atoms are present, same number of octahedral voids are there. That just now we saw that hint. Okay. 4 atoms are having 4 octahedral voids. Then one atom having how many voids? 1 can be multiplied with 4 and divided with 4. This is called a cross multiplication. 1 multiplied with 4 divided with 4. So that 1's are 4 by 4. This will be 1. Means octahedral voids per atom. Octahedral voids in entire CCP are 4. But in CCP, octahedral voids per atom are only 1. And in the similar manner, tetrahedral voids are 8. 4 atoms are having 8 tetrahedral voids. 1 atom having how many? Then 1 multiplied with 8 upon 4. 1's 8 upon 4, so that you will get a 2. In CCP, number of tetrahedral voids per atom are only 2. Total number of tetrahedral voids are 8. Per atom, that will be 2. So that 1 octahedral, 2 tetrahedral voids per atom. Number of octahedral and tetrahedral voids per atom are 1 and 2 respectively. That is perfectly correct. Let's go with unit cell edge length 2 root 2. Atomic mass of CCP for silver. If you are taking silver as the CCP lattice for your specimen reference, so that its atomic mass is denoted as a 408.6 picometers. Unified mass units are provided over here, 107.9 unified mass units. And X-ray studies indicates that the crystal show the edge length of unit cell is 408.6. This is the exact value of unit cell edge length. But the question is, you have to go for the comparison with respect to the radius. What is the edge length? So if you consider this radius, what is the relation between the radius and unit cell edge length? That is given by root 2 under root 2r. Edge length L is equal to 2 under root 2R is the formula. That is exactly given. Unit cell edge length 2 under root 2 times the radius of the atom. Radius for R, edge length for L. So this is the correct answer they mentioned. So for question number 4, option B, option C, option D are correct. This is the question given from solid state chemistry. And this is purely physical chemistry part. Let's go with another question. Question number 5, collected from IMSET examination conducted in the year 2022 by Telangana government. This is called IMSET entrance examination. The correct order of delta FH naught values for diamond, graphite, and fullerene are. Okay. Delta FH naught denotes what? Delta FH naught denotes enthalpy of fusion. Enthalpy of fusion to be understood. Okay. So here all three are said to be allotropes of carbon only. You are going to compare the enthalpies of fusion for diamond, graphite, and fullerene. In order to answer, fullerene comes first, later on diamond will be there, and the least is accorded for graphite. Let's see how can we answer this. The correct option is delta FH naught of fullerene will be higher, and the next will be given for diamond, and the least is given for graphite. Graphite thermodynamically more stable allotrope of among all the carbon allotropes, so that its delta FH naught is taken as 0, arbitrarily fixed as 0, being it is highly stable. And the quantification values of the diamond delta FH naught is given by 1.9 kilojoules per mole. And for fullerene, it will be 38.1 kilojoules per mole. Among all, highest quantities accorded, 38.1 is given for fullerene. So that put fullerene at front. Fullerene is 3 Roman numeral, so that put over here. And diamond accorded with the 1.90, so that move on to 1.90 diamond. Graphite is 0, so that put at least. This is the way all the quantification values are provided, so that you can easily answer this question. Okay, this is the kind of question collected from the thermodynamics point of view. So for question number 5, option number 3 is the correct answer. Let's go with the question number 6. Question number 6. Which of the following lacks hyperconjugative stability? Hyperconjugation is the fundamental phenomenon which is used to explain the intermediate stability. That might be carbocation, that may be carbanion, carbon-free radical, whose stability is clearly mentioned with the concept called hyperconjugation. Hyperconjugation is a permanent effect. And if you go with this CH3, CH2, ethyl carbocation, tertiary butyl carbocation, isopropyl carbocation, methyl carbocation, among 4, whose hyperconjugation is 0, lacks hyperconjugative stability, means hyperconjugation effect is 0, that to be determined. Obviously, D option can be taken over. That D is provided in the option 3. How can we answer this? How can we justify? Let's go with the clear explanation, right? So first of all, hyperconjugation denotes what? Hyperconjugation is the kind of permanent effect whenever carbocation having vacant orbital is in direct contact with the alpha hydrogen. Any carbon containing directly linkage with the positively charged carbon is called alpha hydrogen, and the alpha carbon and hydrogens laying on that are called alpha hydrogens. These alpha hydrogens are able to generate a kind of bonding between, because the electrons whichever contributing the sigma bonding among the carbon and hydrogen will shift, will resonate, will shift towards this bond, so that here carbon double bond will be originated, and no bond will be existing between hydrogen and carbon, so that H positive will remains. This is also hyperconjugation, alternatively designated as a no bond resonance. Why it is called no bond resonance? Because sigma bonded electrons contributed for the stability for delocalization, and After delocalization, bond disappears and no bond existing between carbon hydrogen. Hence, we can consider. Alternatively, term it as a hyperconjugation is termed as a no bond resonance, right? So this is applicable whenever alpha hydrogens are present, then only that no bond resonance is applicable. More the alpha hydrogens, more the hyperconjugative structures. Hyperconjugative resonance is equal to number of alpha hydrogens existing on the carbon atoms. And if you go with this carbocation, the adjacent carbon is called alpha carbon, and possible alpha hydrogens are 3. So that it will contribute 3 hyperconjugative resonance structures. And go with the compound 2. Carbocation is accompanied by 3 carbon atoms in adjacent. So that 3 alpha carbons are located and they are contributed with 3 hydrogens, so that 9 alpha hydrogens are there for hyperconjugation. Highest stability accorded for tertiary butyl carbocation because of higher number of hyperconjugative resonance structures. 9 resonating structures, no bond resonance, are available for tertiary butyl carbocation, so that highest stability. And go with this option C, isopropyl. Around this carbocation, this side carbon, they are contributing 6 alpha hydrogen, so that 6 possible hyperconjugative resonance structures are possible. 9 highest, next level 6, next level 3, and here if you observe, carbocation is no way linked with any other alpha carbon. Alpha hydrogens are not present, so that no provision for alpha hydrogen no bond resonance, so that hyperconjugation is not applicable, being alpha hydrogens are absent. So that option D, no alpha hydrogens, no hyperconjugation. Lacks means no way possibility. That is applicable for option D. That is clearly mentioned over. So by this no bond resonance, the mechanism is illustrated. And question number 6, option 3 is the correct answer. By this, we entirely gone through the detailed description for the session. All the questions are more informative, and definitely you will crack the exam, whatever you are aspiring for. And these are the kind of sessions what we are creating are very much fetching for your coming examinations. So go with the series of sessions, whatever we are conducting on the daily basis, so that definitely you will crack the exam, and highest quality knowledge you will imbibe by following these kind of sessions. So that I'm sincerely requesting you to like the channel and comment. In order to comment in terms of hyperconjugation, can you draw the hyperconjugative structures for phenyl, methyl, carbocation? Let me repeat. Write the hyperconjugative structures for phenyl, methyl, carbocation. This is the kind of carbocation only. How many possible hyperconjugations are possible? You have to illustrate. That is the question for the comment box for the session, and share with the parents who are serious about the examination. Subscribe the channel so that we will go for a new content in the near future. Definitely you will get a high quotient of the knowledge by these series of sessions. Thank you one and all for your patience.